Hello, students. Welcome back to our third session. Third session is errors and types of errors, the error analysis that we'll discuss. So here, the first we'll see the content. The sensor error sensor calibration techniques is the next topic we are going to discuss, and we'll see different types of sensors. Errors in measurement. Already we have seen what is error in our last first class, that is first session. The difference between the mean of set of readings on the same quality characteristic and the true value is called as error. So in a nutshell, it is defined as measured value minus true value. Less the error, more accurate is the instrument. Any measurement carefully it is conducted is subjected to measurement errors. Therefore, errors make it difficult to ascertain the true value of the measured quantity. So that is the error. Error is uncertainty. So uncertainty in the measurement is known as error. So errors can be grouped, or errors can be expressed in two ways. One is absolute error and other one is relative error. Absolute error, again, it can be grouped into two ways. One is true absolute error and another one is apparent absolute error. So absolute error is the amount of physical error in a measurement. So amount of error is here called as absolute error. True absolute error is the algebraic difference between the results of measurement to the true value of quantity measured is called true absolute error, whereas apparent absolute error is the algebraic difference between the measured values of series of measurements and the arithmetic mean of measured values in that series. So here you have to take a set of readings, then you can find out absolute error by finding out arithmetic mean. So how to find the statistical values we will see in today's session itself. Relative error. Relative error is error gives an indication of how good a measurement is relative to the size of the thing being measured. So here the comparison may be true value or conventional true value or arithmetic mean for series of measurement. So relative error is the ratio of absolute error to measured value. So this is the simple definition of relative error. So errors can be grouped like this: static error, instrument loading error, dynamic error. We'll see more further classification of errors. So under static errors, we have reading errors, characteristic error, environmental errors. And under instrument loading error, we have loading errors, environmental errors. Under dynamic, systematic errors and random errors. So apart from this, we have one more classification: types of errors in measurement: gross error, measurement error, blunders. So again, measurement errors are classified into two groups: systematic error, random error. So here these systematic errors are four types: instrumental error, environmental error, observational error, and theoretical error. So these are the classification of errors. The first one, grass error. Grass errors are caused by mistakes in using instruments or meters, calculating measurements, and recording data results. And the best example of these errors is a person or operator reading percentage gauge 1.01 Newton per meter square as 1.10. So this is the grass error, Newton per meter square. At a later time of taking down reading, writing and calculating, and then presenting the wrong data, thus producing deviation in results. So this type of error is known as gross error. Blunders. So blunders are the final source of errors, and these errors are caused by faulty recording or are due to wrong value while recording a measurement, or misreading a scale, or forgetting a digit while reading a scale. So this is a blunder. It is also by human beings only. These blunders should stick out like a sore thumbs. If one person checks the work of another person, it should not be comprised in the analysis of data. So blunders are again due to human faults. Measure, measurement errors. The measurement error is the result of the variation of measurement of the true value. The best example of measurement error is electronic scales are loaded with 1 kg standard weight, and the reading is 2 grams extra to the kg. Then the measurement error is 2 grams. So measurement errors are again systematic error and a random error. So systematic errors are also known as controllable errors. The systematic errors that occur due to faults in the measuring device, usually they are called zero errors, positive error or negative error, or both are possible here. These errors can be detached by correcting the measurement device. These errors may be classified into different categories such as instrumental errors, environmental errors, observational errors, theoretical errors. So instrumental errors, these are due to wrong construction of measuring instruments. So this will definitely due to hysteresis or friction in the measuring instrument. That is instrumental error. And we have different instrumental errors and causes. Here, error of a physical measure, error of a measuring mechanism, zero error, calibration error of a physical measure, complementary error of a measuring instrument, error of indication of a measuring instrument, error due to temperature, error due to friction, error due to inertia. So these are all the causes of instrumental errors. Environmental errors, this we cannot avoid in these are due to ambient conditions. These errors result from the effect of surroundings such as temperature, pressure, humidity, etc. on a measuring system. External influences like magnetic or electric fields, temperature, humidity, and nuclear reaction, vibrations or shocks, etc., etc., also leads to environmental error. It can be reduced by controlling the atmosphere according to the specific requirements. So here it is possible to minimize this environmental errors by having the controlled environment. And then we have observational errors or reading errors. So here the reading viewpoint where you stand and read, that matters here. Reading errors are apply exclusively to the readout device. These do not have any direct relationship with other types of errors within the machine system, which include it is the major error is due to parallax error. It is the error which arises due to incorrect positioning of the eye. So incorrect positioning of the eye will cause this error. So here is the object. So this is the view obtained from point B. So when you stand here and see this object, this will be observed here as red. The object is viewed as red object. Whereas when you stand here and if you observe this object through this plane, then this will be viewed as a blue one, right? The object is on blue background. So this is known as parallax error. So actually there is no color, it is a transparent one. It is a real view. The object is actually only having yellow color. Its original color is yellow. It should be observed on this as without any color background. So that is the parallax error. So you can see the parallax error here, and this is the reading, and you are measuring exactly 19 centimeter, 19 centimeter, and when you exactly see perpendicular to the scale, right? Your viewpoint is 90 degrees to this scale, and here when it is not at 90 degrees, then there will be 21 centimeter this side, 1 centimeter more, and this side 1 more centimeter. So this is the parallax error. So this is another example for parallax error. Theoretical errors are simplification of model system. For example, a theory states that the temperature of the system surrounding will not change the reading. When the readings are taken, then this factor will begin a source of error in measurement. So theoretical errors are simplification of model system. So these errors are due to the theoretical development of model, and this can be minimized with the utmost care. You can minimize theoretical errors. Random errors. Random errors are non-consistent. They occur randomly and are accidental in nature. Such errors are inherent in a machine system. It is difficult to eliminate such errors. Their specific cause, magnitudes, and source source cannot be determined from the knowledge of measuring system or conditions of measurement. The possible source of such error is small variations in the position of setting standard and workpiece, slight displacement of lever joints of measuring instruments, operator error in scale reading, fluctuations in the friction of measuring instrument, etc. etc. These are all the sources for these random errors. So this accidental in nature, so we cannot avoid this type of errors in routine measurements. So, so coming to error analysis of measurement data is necessary to obtain the probable true value of the measured quantity. Any measurement is associated with a certain amount of uncertainty. The best method analysis is statistical methods. So statistical methods gives the best result analysis, that is error analysis. For statistical analysis, a large number of measurements are required. Also, the systematic errors should be small compared with random errors. So the error analysis can be performed very effectively using statistical methods. We will see the different components of statistical methods. For statistical method, the terms like arithmetic mean, deviation, mode, and median are to be determined. So here, these are the components of statistical methods. We need to determine this. And here, arithmetic mean, the most probable value of measured variable is the arithmetic mean of number of readings taken. You are taking number of readings, and you are finding the mean value of all the readings that you have taken. So that is arithmetic mean, and arithmetic mean can be calculated x1, x2, x3 up to xn, n number of readings, and divided by n. So how many number of readings you have taken, that number should be the denominator. And deviation is departure of the observed reading from the arithmetic mean of the group of readings. Let the deviation of the reading x1 be d1 and that of the x2 be d2, etc. Then d1 equal to x1 minus x, and d2 is x2 minus x, and dn number at infinite number xn minus x. So average deviation can be calculated using by mod of d1 plus mod of d2 plus up to dn divided by n. How many number of readings you have taken, that is your n. So this is how you can calculate deviation and average deviation. Standard deviation, another term in statistical analysis of random errors, is the standard deviation or the root mean square deviation. So root mean square deviation is also another name for standard deviation. The standard deviation of an infinite number of data is defined as the square root of the sum of individual deviations squared divided by the number of readings. So standard deviation can be calculated using this simple relation. Next, variance. Variance is another term which is sometimes used in statistical analysis. This is the square of standard deviation and is given by, this is variance v equal to sigma square, and this is up to 20, right? Up to 20 can be divided by n, d1 square, d2 square, up to dn square divided by n. So where for n greater than 20, and this is the same relation, it is sum of dA square divided by n minus 1 for n lesser than or equal to 20. So this is the variance formula, and it is characterized by some number. It should be it is 20. It can be taken, this formula can be used if it is more than 20. This formula can be used if it is lesser than 20. Median is also used to indicate the most probable value of measured quantity when a set of readings are taken. So here, when the readings are arranged in ascending or descending order of magnitude, the middle value of this set is taken as median. So the middle value is taken as median. For example, the temperature of a bath is noted by 10 observers as below. So you have all these numbers in ascending order, and now the median is 75.5, right? So here it is arranged in ascending order. After arranging this, and 75.5 is the value at middle, and that is taken as median. So now this is the median value after arranging in ascending order. You can arrange in descending order also, you can find the median. Mode. Mode is the value which occurs most frequently in set of observations and around which other items of the set cluster. For example, the frequency distribution of a set of 100 observations is given below, and you have these readings, and number of readings are here. These are the temperatures and number of readings. The value of temperature reading 33 has occurred 25 times maximum, right? So 33 is happening 25 times. So this is the 33 happened 25 times, hence mode is 33 degree. So 33 degree centigrade. So this 33 is happened 25 times, so that becomes mode, maximum number of times. So this is how you can calculate mode. Next, statistical methods for analysis. Probability of errors. This is the first method. By the nature of the random errors, the uncertainty associated with any measurement cannot be predetermined. Only the probable error can be specified using statistical error analysis. The following are some of the statistical methods of analyzing the errors. Histogram is one way to analyze the error. When a number of multi-sample observations are taken experimentally, there is a scatter of the data about some central value. One method of presenting test results is in the form of histogram. The technique is illustrated, shows as a set of 50 readings of a length measurement. The most probable central value of length is 90 millimeter. So this is the table, 90 millimeter, and it is happening. Number of readings taken 19 times. So histogram 90 happened 19 times, and this is the histogram for this values. So histogram can be drawn like this. It is a graphical representation of error analysis. Normal or Gaussian curve of errors. This is another method. Normal or Gaussian errors is the basis for the major part of the study of random errors. So random errors can be analyzed using Gaussian curve of errors. The law of probability states the normal occurrence of deviations from the average value of infinite number of measurements or observations can be expressed by this relation. This relation y equal to h by root pi exponential of minus h square and x square. X is the magnitude of deviation from mean. Y is number of readings at deviation x. the probability of occurrence of deviation x, and h is a constant called precision index, and here this is the distribution, normal distribution curve, normal probability curve. So this is how it can be represented. So probable error, the most probable or best value of a Gaussian distribution is obtained by taking the arithmetic mean of various values of the variance. The confidence is in the best value, most probable value, is connected with the sharpness of the distribution curve. So this is a probable error, and there the error analysis can be done in the above ways, and we have the textbooks, and we have e-resources. We stop here for error analysis, and we'll start the calibration techniques in next session. uh, thank thank you students. We will see in next session.